In this video, we're going to talk about the general properties and definitions of acids and bases. So when you think of an acid, you should think of something sour, like if you bit into a lemon. That has a very acidic taste. But acids also have other properties. They change the colors of indicators, so acid-base indicators. We did a demo the other day where we put universal indicator in, and when it was in an acid, it turned like a nice red color, and then when it was a base, it turned all the way to blue, and it turned all the colors of the spectrum in between. We've also done demonstrations and activities where we've used phenolphthalein, an acid-base indicator that turns pink when it's in a basic solution, and a nice clear color when it's in an acidic solution. So it also can change litmus paper and turn it into red litmus paper. It also acids can react with metals to generate hydrogen gas. We've done that when we did the molar volume of a gas lab where we reacted magnesium metal with hydrochloric acid and we produced hydrogen gas that we then measured and analyzed. Acids also react with metal oxides and hydroxides to produce water and salts. Now, a common reaction would be hydrochloric acid, which is an acid, obviously, by the name, reacting with sodium hydroxide, which is a base, to form water and a salt. Not all salts are NaCl. That is just one of them. The actual definition of a salt is the byproduct of an acid-base reaction. And then I just want to point out that both acids and bases conduct electricity when in solution. So, properties of bases, they taste bitter. They don't taste sour. If you want to know what a base tastes like, just bite into a bar of soap. Wasn't that fantastic? Thought you'd agree. They also feel slippery like soap. Soap is actually basic. It has a pH of around 10. Bases also change the color of indicators. Bases turn litmus paper blue. So acid, red, base, blue. And they react with acids to form salts and water just the same way. And they conduct electricity. Real quickly, I'm just going to show you what that looks like. When I put these electrodes in water, you have electrons that want to move across the solution. That's what electricity is moving electrons. And when you have ions, particularly cations, present in solution, you give a path for the electrons to hop their way across and complete the circuit, allowing for the conduction of electricity. Both acids and bases, we said, were conductors of electricity. So a strong acid will allow you to really conduct electricity. And the reason is, when you put an acid in water, it's going to break apart and give off that hydrogen. That's what acids do. That hydrogen then gets absorbed by water, and it's considered to be a hydronium ion, which you can see right here, and you're left with something called a conjugate base after. So we'll get into another detailed video about conjugate acid-base pairings. But for now, you just need to know acids give off an H, and then water carries that around. So sometimes you'll see the dissociation of an acid written as like HCl becoming H plus and Cl minus. But really what's happening, because it's in solution, is it's going to interact with the water and form a hydronium ion, and then you still have the chloride. These two terms are used interchangeably all the time. So when you see one, think of the other as well. Bases also dissociate, and you get positive and negative ions. The ion that's produced by a base is the hydroxide ion. So acids will contribute to the increase in the concentration of the hydronium ion or the hydrogen ion, and bases will result in an increase in the concentration of a hydroxide. Now, strong acids will dissociate 100% of the time, and you can see that. There's no unionized version of it. However, a weak acid, such as like vinegar or citric acid, or most of the organic acids that we see in our world, only a small portion of the molecules actually ionize. Most of them remain in the gray form you see here, or unionized, and very few break apart into the ionic form. Hence, it doesn't conduct electricity as well, so we would consider that a weak electrolyte. And the same deal for bases. If you have a strong base, it's going to dissociate 100% of the time. Notice I said dissociate for a base. Because it's an ionic compound, we have a positive and negative thing that are already positive and negative in separating. When we're talking about an acid, we have a neutral molecule where electrons get removed from the hydrogen and it ends up forming an ion. So we use the term ionization for an acid and dissociation for a base. But you can see here that a strong base will dissociate 100% of the time. Hydroxides that are very soluble, according to your solubility rules, will make strong bases. Weak bases, on the other hand, they'll only produce a hydroxide some of the time. And when you have that, you have a weaker conduction of electricity, and therefore a weaker electrolyte. So now let's look at the three different definitions you need to know for acids and bases. Acids, in general, I want you to think of acids as being H plus donors. And I want you to think of bases as being H plus acceptors. And that would be the Bronsted-Lowry definition. But before we got to that, we had the Arrhenius definition of acids and bases. Acids are H plus donors, and bases are hydroxide donors. But what we end up finding out is that not all bases, or things that result in a pH higher than 7, contain hydroxide within the molecule. An example of that would be ammonia. Ammonia is capable of removing it doesn't have a hydroxide on it, so it can't donate a hydroxide. But when you put it in water, it's capable of accepting a hydrogen from water and then leaving behind a hydroxide ion. So it would increase the pH of the solution because of that. So it didn't fall under the category of Arrhenius acid, but it does fall under the Bronsted-Lowry definition, which calls a base an H+ acceptor. Now, going a little bit further, there's also the Lewis definition, and this is the most inclusive definition of acids and bases, and this covers pretty much everything, but this covers the vast majority, and conceptually that's how I'd like you to think of it. But a Lewis acid will be an electron pair acceptor. An example of a Lewis acid right here would be BH3. You can see that it only has 6 electrons in its outer shell, and really we all know atoms want to have 8 electrons in their outer shell. It's a complete direct tet rule. So what it can do, it can react to something like ammonia, which has an unshared pair of electrons, and then it'll end up forming a coordinate covalent bond there. But what it did in that process was it ended up essentially neutralizing a base, meaning it had to be acidic, and it was an electron pair acceptor in that case. So we've covered some basic properties of acids and bases. We've looked in general at electrolyte systems that they form and the definitions of these things.